Okay, for the record, today is March 1st, 2017. I'm Gunter Steinbach interviewing Gary Gordon in what I would call his natural environment, that is sitting at his workbench. Thank you, Gary, for agreeing to let me interview you.
Thank you.
And I originally contacted you because one of your 80 patents describes the modern optical mouse for the first time. But we will not limit ourselves to that. We want to cover your whole life and career. And as you can tell from the number 80 patents, there's a lot more that you've done in your 38 years at HP. So let's start with the beginning.
Hey, thank you for the nice introduction.
What's your family background? Where did you grow up, and how did you get into electricity and engineering?
Okay, well, I was born in Portland, Oregon in 1939 and spent my younger years in Spokane. And I think probably about the age of 6 or 7, I really got interested in taking things apart. I had motors, forward induction coil, fans, buzzers, and I really enjoyed figuring out how they worked. And generally that amounted to taking them apart, and that was where they ended up. My dad had an electric train, and I thought that was quite uninteresting to watch it go around in a circle, so I would go back to my corner and play with my toys.
So then you moved to near Spokane.
That was in Spokane. At the age of 10, we moved to Milwaukee, which is on the outskirts of Portland.
Okay.
And that's when my building really started. I had my room off of the garage, which was away from the family and all the distractions. And my friends would just build things. I built 2 Tesla coils, an oscilloscope. I ground the mirror for an 8-inch telescope, and I just really thrived on creating things mostly mechanical. And then eventually I got into ham radio.
Okay. So tell us about ham radio.
Well, that was a cool hobby back then. It was a time when it cost $1 a minute to talk across the country. We could, using equipment we built ourselves, talk around the world for free. And we could have radios in our cars. So it was quite a neat hobby. This is a picture of my station, one of the few pictures of my childhood, but I either built from a kit or from scratch almost everything in that picture.
Wow, it's was always beyond my means, and radio. But anyway, you joked that you were raised by the principle of benign neglect.
Yes, my parents were quite indifferent to all these technical pursuits, and so being left alone, I had to figure things out for myself. And I really appreciate that, because I think it led me to be a sort of an inventive person, and I would recommend that as a good way to raise children.
So you didn't, your family background was not actually engineering. That was something you started with.
I was from a typical family. My dad was an accountant, and he had 2.3 children. You know, that was or at least that was the average background for an engineer at the time.
Okay, so you said you knew you wanted to go into engineering, right? Where'd you go to school?
Yes, that was pretty clear that I wanted to study electronics, and I applied to a number of colleges, and I was also aware of the inevitability of having to serve in the military at some point. So I applied for a couple of scholarships, and one that I got was the 4-year Naval ROTC scholarship. And at the time, my family was moving to California, so I enrolled at University of California at Berkeley, studying engineering.
So that was for undergrad in Berkeley.
Yes.
And anything interesting from from that time? Like a
I,
summer job?
I think I'd like to mention a summer job. I really wanted to work at Hewlett-Packard, and went down after a couple of visits and asked them how my application was coming. And the personnel manager was a lady, and she said, well, I've given the engineering manager about 100 resumes, and they just sit on his desk. And I think I'm going to march you in there and say that that you're the choice, and unless he has some objection. And he just assumed that I was a summer hire, and so I worked on sampling oscilloscopes, and I just loved it. I would do basically technician work, whatever they had in mind. I just thrived on it. And toward the end of the summer, they were running out of things to do for me to do, and they said, why don't you go build a hi-fi set or an amplifier or something, or you can work on this problem with a sampling oscilloscope. I said, well, what's that? And they said, well, when we change the sweep rate of a sampling oscilloscope, the baseline jumps around, and this is very embarrassing. And so I looked at that for a while, and I realized that it was caused by the sampling diodes. And it would vary with how fast the sweep rate was set, and different diodes would jump different amounts. And I thought, well, I'd like to characterize them. So I wanted to build a sweep generator, and the only way I knew how to do it was a 4-layer diode and a motor-driven potentiometer, which was really crude. But I could change the sweep rate and see on the trace of the oscilloscope the point at where the baseline jumped and the amount that it jumped. And each diode was different, so I sorted them into a two-dimensional matrix of egg cartons. And I found that if I took 2 diodes out of the same bin and put them in the probe, that the problem largely went away. And so they were actually delighted with that. And I was just about to ready to go back to school, and the lab director was very complimentary, and he said, do you have an oscilloscope? And I said, well, of course I have a Heathkit 3-inch scope. And he said, well, we can do better than that. And so he walked around the lab, and I wasn't sure what he had in mind, but he asked an engineer, he said, does this scope up on the top of your bench get used much? And I said no. And so he took it and gave me this wonderful HP oscilloscope. It's kind of a going away present. So awesome. That was the main thing I remember from my college days.
Okay, so and then what about after graduation?
Well, I had to face the consequences of my Navy scholarship, and I got married to my wife, Nicola Whitney, and unfortunately got sent off on a ship. I was the radio officer on an aircraft carrier. Things improved after about 2 years. I was assigned to Treasure Island. It was this top secret facility that kept track of Russian submarines in the Pacific Ocean. They used hydrophone arrays up and down the coast and in Alaska and Hawaii. And all this information from these arrays would get collected and sent to Treasure Island and put into IBM holorith cards. And they really didn't know what to do with them. And they also had an IBM 1401 computer. So I went to the IBM school and learned how to use the thing, and wrote some programs that would organize the sounds they picked up, decide which ones were Russian submarines, help present the data. And so that was actually fairly interesting to do.
That sounds like the Tom Clancy thrillers, right?
Sounds like what?
Like the Tom Clancy thrillers, Hunt for Red October. And so
well,
on.
Well, we did a lot of things that Clancy later wrote about, tracking Russian submarines and playing dirty tricks.
Okay, so so you had to do 4 years in the Navy.
Yes, and then when I got out, I was eager to work at Hewlett-Packard, and actually, while I was in the Navy, I would still build things. I had a workbench, and I wanted to show this. I'd taken some transistors and built some multivibrators and made a key that would generate sequences it would improve the way you could send Morse code. So I could send sequences of dots and dashes, and so to send code, you'd see if I can do this right. That's a little too fast. So that was, so I took that to HP for my interview, and they said, well, it says here that you're pre-approved for hire, that we just need to decide which division you want to work in. So I decided to work in a division called Frequency and Time. They built frequency counters. Being interested in radio and shortwave, I thought that counting frequency was quite an interesting concept. And they asked me to work on a thing called a computing counter. They pretty much owned the counter market, and to grow it, sometimes they said, well, there's a need to have computation associated with counting. Example would be if you're measuring a frequency of a slow-moving signal, such as the line frequency, we would measure the period instead of the frequency, and you'd want to convert that to frequency and take the reciprocal of your reading. So that was just at the time when ICs were coming into vogue, and so this computing counter was actually the first instrument at HP that used integrated circuits, and it was...
What year was that?
It would have been about 1970. And they were, or a little earlier, and they were known as SSI, or small scale integration. Basically, a device would have 4 flip-flops in one small DIP package, and of course, you think of that today, we have terabytes of terabytes. This 6 bits was half a byte. Now you have terabytes. So yeah. This was really small scale integration, and it was actually required a whole different approach to designing, because we would look at these circuits and you'd have these long bit streams that basically you couldn't even make any sense out of on the scope because they all looked alike. And so we evolved the system of testing that we would call single stepping, where we would hand clock I should say the arithmetic unit was 12 digits, and it had 2 digits of exponents. So it was a floating point processor that would add, subtract, multiply, and divide, and take square roots. And I think what I'd like to comment on is the testing we evolved, which was entirely different than the analog testing of the scopes and the previous HP instruments were designed to be used for. So we would single step them, and I found it is almost as useful to go around with a little light bulb on a wire and look at states change than to try to see them on a scope, because I didn't have to turn my head. And I eventually evolved that into what I called a logic probe, which I'd like to, I have one still. This, and this would be a circuit with a typical small scale integrated circuit in it. This was a 4-bit counter. So if we want to look at, so basically the logic probe would show it would be half lit, and it would show high states by lighting to a higher level and low states by extinguishing. And so if you looked at one of the bits of the counter here, this has a 1 hertz clock generator, and so this is a divide by 2 pin of the counter. And if you look at the divide by 4 pin, it doesn't change state quite as fast. And I thought, well, I'd really like to look at pulses because they're too narrow to see on a scope. And so I put stretchers in this, and I thought, well, I want to see positive pulses and negative pulses. So this, if you have a positive pulse here, this is coming from the clock of the circuit. It momentarily extinguishes, so that means that there's negative going pulses on this pin, and positive going pulse would do the opposite. It would cause the light to flash. And this got the attraction of the division manager, and he said, well, let's just see if we can sell these things. And so we put in the catalog, and these things sold like hotcakes. And in fact, you can still buy them today, but they're mostly used by hobbyists. So we thought, what else would we like to do? Well, one thing you'd like to do is to interject pulses into a circuit. And so I won't demonstrate it, but this is basically a logic pulser. And again, I wanted to be a little bit clever so that if you put it on a pin that's high and pulse it, it drives the pin low. But if you put it on a pin that's low and pulse it, it drives the pin high.
Okay.
And that was a success. And then we thought, we're just kind of free thinking, what can we do? And he said, well, what if we want to look at a lot of pins at the same time? And someone had come around with the first LEDs that had ever been built, and this is again around before 1970, and so I thought, well, we can put these in a little clip-on device and clip them on top of the circuit, and watch the pins change state. And I always like to do something a little bit out of the ordinary, so I didn't want to have a wire on it to hook into 5 volts and ground. So I have it seek out the voltage and self-power. So if you put it on upside down, it doesn't really care which way it's put on. It works either way. So to continue on this, I wondered about digital service, and I had remembered days of seeing schematics of things like television sets, and they would have little miniature waveforms on the collectors and emitters of the transistors, and you would basically use signal trace. You would trace the signal up to a point where the signals were good, and then on the other side of the device, if they were missing, you'd isolated the problem. So the problem with doing that in digital is the wave shapes all look the same on oscilloscopes. They're just meaningless long streams of data. So I thought, well, let's do a checksum. This is a CRC checksum hexadecimal that we can measure and write on the nodes. So if you have good data coming into a device and bad data going out, then you've identified the faulty device. And we called that product a signature analyzer and sold that for a while. And maybe I'll just kind of summarize the state of digital testing, because this only lasted about 10 years. This was before computers and simulation, and it wasn't too long after that that you wouldn't have to fuss around with the single stepping. You would simulate everything on a computer or use state machines or ROM arrays. And so basically this was, the first decade of digital design was single stepping, looking at individual states, logic probes and the sort.
And so basically you got HP into that business of
I would
the
say
logic
so.
debug
Yes,
instruments.
and we patented these things and we gave them names. And so we see something like a signature analyzer. Well, what is that? Well, we just pulled the name out of the air.
Okay, and the logic analyzer would be a similar instrument also with,
yes,
with a screen.
That finally, we realized that you could have a sort of digital analogy to an oscilloscope and show the bits on light emitting diodes, and you could do a lot of other things too. This would be a storage scope. It would also capture triggers. You could have the data coming in and then have a trigger, and you could see the data that led up to a trigger, which is a lot simpler than the delay lines that you would have in oscilloscopes. So now this started to get the attention of Colorado Springs division that made oscilloscopes, and I wanted them to build a digitizing oscilloscope, but instead they saw this and they thought, no, we're going to build logic analyzers. And my experience was with the HP35 and serial computation, so we didn't have very many channels. They were near the Levelland division that built a desktop calculator that used a 16-bit wide word. And so they built a wider analyzer and pursued that line aggressively, and that was the right place to do it. And so, of course, you can still see logic analyzers made today.
Okay, so were you offered managing jobs in that area?
I actually, the next project after that was a laser interferometer, and I did manage that project. Let me talk about that. That was a very interesting project because it involved optics and mechanics. Basically, we counted the wavelengths of light to measure distance, and we built this instrument that would measure distance out to 200 feet to a resolution of a millionth of an inch. And it was we're not the first people to introduce one. There were 10 other companies, but the main competitor was Perkin-Elmer, and we had a really wonderful laser in ours that was designed by the labs, and it was piezoelectrically stabilized, so it would stabilize in a second or two, whereas the Perkin-Elmer laser was thermally stabilized, and it took an hour and a half to warm up. So they would go into customer and try to do a demonstration and have to talk about something else for an hour and a half while this tube was warming up, and ours would just turn on instantly. You flip the switch and it was measuring distance. And we did several other cute things in it. One was their interferometer, basically all the other ones measured resolution to 6/millionths of an inch, which is a quarter wavelength of a helium neon laser. I added digital signal processing that would interpolate that down to 1/millionth of an inch. So we could go into a customer and turn it on immediately and measure to 6 times the resolution, and basically we just took over the market for that product. That was a lot of fun. That was one of my most favorite projects to work on.
And nowadays, of course, they are still used in all the wafer steppers, right? These.
Well, that's a good point. That's actually, this would not work for wafer steppers because it took 10 milliseconds to do the conversion from wavelength to English or metric units. And steppers in the integrated circuit industry have to have feedback loops that have practically no delay at all. Mm-hmm. So what they do is, instead of converting to microns and closing the feedback loop, they compute ahead of time how many wavelengths of light they want to go to a certain position, and then they close the loop in wavelengths. So basically, a lot of the features in this interferometer are not really necessary. So that was a simpler product, and I was kind of losing interest in that. So someone else did that, but that's a big market for HP, which has turned into Agilent and Keysight, I guess. But one of these companies to this day still makes these products.
Okay. And along the way, you also got a master's degree, right?
Yeah, that was an honors co-op program at HP. They would send you to Stanford, give you time off, and pay the tuition. So I very much appreciated that.
Okay, and you mentioned a mouse contest, which is not the optical mouse.
Well, that's probably a little embarrassing for the IEEE. They had microprocessors were just starting to come on the scene, and they had established a contest to build a microprocessor navigated mouse that would go through a maze that they had built. And I read about that, and so I kind of talked to the guys I was working with. I said, you don't need a microprocessor to do that. If you follow the right wall, you'll eventually get out of this maze, and you can probably do that pretty fast. And so they liked the idea and built a mouse, and I mean, I didn't get too involved with it, but they took it down to LA and competed against Battelle Institute mouse that actually had a microprocessor and lumbered around and eventually, I think, solved a maze. But our mouse solved it, I think, in a third the time. It would just basically keep banging against the right wall, and so I gave it the name. Well, there was a popular drink at the time called a Harvey Wall Banger, so that was the obvious name for our mouse. And that got printed up in Reader's Digest, so it.
Cool.
That's that story.
Okay, and you went on eventually to end up at HP Labs.
Well, HP had wanted me to be on a career path through management, and I think it was becoming evident to me and maybe to them as well that I'm really a designer. I really like solving problems and rather than working with people that much. And so I went up to HP Laboratories, Central Research Laboratory, and they wanted me to work in analytical chemistry instrumentation, which I thought, well, I'll do whatever they want. And I did that for 25 years, making parts of a string of instruments that would look for environmental contaminants, do DNA identification, and so forth. So it was fairly interesting, quite a bit different than the things I'd done. But I can mention two of them. One I liked was we had an instrument called the capillary electrophoresis instrument, and it would basically look at environmental contaminants, for example, and separate them in a long capillary tube and the inside diameter of the capillary was about the diameter of a human hair. And you would detect the chemicals that came out of that capillary by basically looking at their color in the ultraviolet spectrum. The problem was that the absorbance path length was really short. And so I remembered as a kid, I had a chemistry set that I didn't particularly enjoy, but I found that it was fun to take glass tubing and heat it over alcohol lamp and blow bubbles in it. So I remembered that experience and tried that in these capillaries, and that worked really well. And so it turned out that even competing instruments in that market would buy the capillaries from HP Agilent using this bubble cell, as I called it. I'm just kind of jumping over some of the projects, but one of them was a robot. It turned out that a lot of chemists were doing very boring things by analyzing thousands of samples and very repetitively, and so it seemed like something that should be automated. And so we built the ORCA robot. And one thing I enjoyed about that was, I think I'll mention one thing here. We wanted to use sort of a game teach pendant to teach the robot how to move. And so obviously if you want to move the robot arm out, you push the stick forward. Want to move it to the left, you push the stick this way. But then how do you lift the arm up? Well, I decided to put gravity sensors in the teach box so that when you turned it like this, it changed what the stick did. And now that move the stick left and right, move the robot back and forth, but you do this and it moves the robot up and down. And of course, somebody would always inevitably say, well, what if you hold it upside down? Well, it still worked.
That's cool. That's very intuitive then. You just turn it so the stick does the right thing, right?
Yeah, it added more degrees of freedom from a stick that only had X, Y on it.
Right. So you did some electronics still even in the chemical analysis side, but
yes,
but
less and less.
It's a huge change in your career, right? From electrical engineering.
Yes, as I'll tell you later, I still did electronics as a hobby, but.
And then you mentioned DNA just earlier. Was that after the chemical analysis you went on to the DNA?
No, well, that was
arrays?
part of it. It was very, very interesting. They had put fragments of DNA on an array and then put a sample on top of it and see where the sample hybridized to the array, and then I identify DNA using a technique. And so I built some techniques for increasing the sensitivity of that, which was just one of the many things that kind of kept me interested in this analytical chemistry and bioengineering.
About what time was that?
20 years ago, around the turn of the century, I guess.
Okay, so that's also the time when HP split off Agilent, right?
Yes.
So then you moved, as I know, since I was there too, you moved to Agilent. You moved along with Agilent to Agilent. Labs.
Yes, and just only thing that changed was the name.
Right. Well, we always thought we were the real HP.
Yes.
Right.
Do you want to talk about the optical mouse, because that was the next thing I worked on.
Okay. And at the time were you already an Agilent Fellow, or?
They gave me that level of. They signed that along the way, so somewhere in there that happened, which I appreciated.
Okay, which is as high as you can get.
On the technical ladder.
On the technical,
right.
Yes.
So I had foregone the management ladder a long time ago.
Okay, then yeah, let's talk about the optical mouse.
I think for several years before I really got actively engaged in that, I used their mechanical mice and was constantly aggravated. And I brought one along because these things are actually very hard to find if you want to locate one, because they've all been thrown away. And maybe 20 years from now, somebody will wonder what the problem was. Well, they would get dirty, and with aggravation, people would slam them on the table and blow on them and so forth. And finally, they would take them apart. It was meant for easy disassembly because it was something you really had to do every couple of months. Clean out the inside, blow it out, or, put the thing back together. And I used this on a wood surface, and I thought for many years that it should be optical because I had seen image target tracking in the Navy. I had studied correlation at Stanford, and there were projects around HP that actually there was a scanner that handheld scanner that looked at its position by using optical scanning. So I thought, if the whole world was wood desks, we'd make an optical mouse, but it wasn't. And my desk surface was Formica, and it looked really smooth, and so I was kind of discouraged. And it was a year and a half later that one time I was kind of lamenting that it couldn't make an optical mouse that would work on the Formica surface, and so I scratched the surface with my finger and could kind of hear this vibrating sound, and I realized that the surface was textured. And then I lit that with a flashlight obliquely, and under a microscope you could see all these hills and valleys. It looked like you were in an airplane coming in at sunset over some hilly terrain. And so I knew bingo, this would work. And so I want to give a little example of how optical mice work, because this is just about not written up anywhere. So I think it's worth covering. The optical mice looks at a area about 2 millimeters by 2 millimeters on the surface. So it's a microscope and a crude image sensor with about 1,000 pixels. So if you look through a microscope at a 2 millimeter square of paper, which I decided to use as an example, it just looks kind of featureless. But if you edge illuminate it at about a 10-degree angle and then increase the contrast, which you can do, suddenly you start to see all sorts of detail on this same 1 millimeter square. So we image this on our sensor, which again is only 1,000 pixels, so it's a fairly crude image, but there's actually a lot of information buried in this. So what we do is we take pictures 1,000th of a second apart as the mouse is moved, and then we slide the two pictures over each other to find the fit. So in this example, the same picture I showed last shows the image taken a millisecond later, and you can see that there is sort of a feature here that tended to move about 6 pixels. And so what we do is slide these two images over each other, it's called correlation, and test the fit. And we slide them over, we don't cover the whole array, we cover maybe 100 pixel. Basically we compute the correlation at 100 positions and keep track of them. And then at one position, you'll see a very, very strong correlation. And this says, well, that's what we expected. The mouse had been moved about 6 pixels on a diagonal. And that would correspond to a mouse movement of, well, 1 pixel here corresponded to about 3,000ths of an inch of mouse movement. And it turns out you actually, for CAD work, you nudge the mouse and want to move even to more like 1,000th of an inch resolution. So what we do is we interpolate between these values and say, well, it wasn't quite 6 pixels, it was maybe 5.7 pixels on the diagonal. So that...
and that works even if the mouse twists a little as you move it, because that tends to change the shape, right?
I think in 1,000th of a second it doesn't change too much.
Yeah.
And this got picked up. I'd also worked on had an idea for what I called a flying mouse, which I thought that at one point that the television set and the computer were going to converge, and I was not correct on that, but I felt that if that happens, you're going to need a mouse to control the cursor on a TV screen. And so we built a flying mouse that would basically image the room, and then as you turned it, the attitude would change, and it would watch that image fly around and tell you the attitude of the mouse. And we had a very brilliant manager in the components group, Jason Hartlove, who tried to market that to the Japanese, and And there was a lot of interest in that, but that was about the same time we were coming up with this mouse thing, and he was kind of headed in the same direction. So we started sort of a frantic effort to build this mouse. I wrote the patent on it at that point and submitted it, and it was allowed, but we put all of our names on it, of course. And basically, it's completely obsoleted, the mechanical mouse, in a matter of a couple of years.
So, but the start of the idea was a mouse on the table, not the flying mouse, or
no, it was a mouse on the table, but all these things float around in your head, as I told you. Military tracking, correlation at Stanford, these other projects looking at navigation by motion, and sometime, I think in your head these things just kind of come together, and you realize that, I should have thought of this years ahead of time. I kick myself for that. But.
Well, it wasn't too late, right?
No.
Nobody else beat you to it.
They sold about 1 billion of them.
Yeah. So what year was that you wrote the patent?
I don't remember years very well.
Okay. Well, it'll be on the patent, I
guess.
Yes. Yeah. So,
that's
okay.
for sure. I might mention that I kept working on mice for a while, and one thing was we could make the sensor so small that I felt that we should be able to put it in a pen or some other device and maybe have better ergonomics with the mouse, but that didn't really catch on. But one thing that did was there was a lot of interest in wireless mice and the power consumption of the batteries that they had to carry. And the main power consuming device was the LED flashing 1,000 times a second, and you had to flash it that often, because if you didn't flash every thousandth of a second, the mouse would move so far that you would have an image that could not be correlated with anything. So I reasoned that we could take a mouse reading, a thousandth of a second later, take another image, correlate the two, and then we don't need to immediately start taking more readings. We can send information to the computer. We can extrapolate that and say, well, the mouse is moving in this direction, and we can just extrapolate where it would be. And then 100th of a second later, take another pair of readings. So we're cutting the LED power by a factor of 5, and that amounted to almost extending the battery life by a factor of nearly 5. So that got used. I think it's probably used in all wireless mice.
Did you patent that?
Yes.
Okay. And that, and it's obviously it wouldn't be used if it wasn't reliable enough, right? I guess there is your arm is pretty heavy, so there's the momentum just makes it a smooth movement.
Yes, a 100th of a second, not too much happens, and it was an engineer in the division, Mike Brosnan, who reduced it to practice, and of course I put his name on the patent application because you can come up with these ideas, but somebody else has to, I knew it would work, but he actually had to make it work, and he did.
Okay, and at one point you mentioned fingerprint sensors.
Well, we realized we could have a tiny sensor in a cell phone or a camera that would sense the fingerprints as they slid across it, and these things worked. I had another idea for adding momentum to a cursor on a screen to where you move it, the cursor keeps going along with its own. That would be used with a touch screen, but these didn't get commercialized.
Well, the fingerprint sensor now is in the iPhone, but it's not optical. Right? It uses,
okay.
I believe it's capacitive, which is kind of amazing because it needs to be very high resolution. Okay, so that was kind of getting close to retirement. Were you eager to retire, or would you have gone on?
Well, I was 63, but something else happened. I quit. I didn't retire.
Okay. And
You
so
wanna know-
now you've been retired for quite a while.
Okay, can I kind of tell you why I quit?
Go ahead if you.
Well, I hadn't had a raise in 5 years, and I went to them and I asked for a raise, and I didn't get one, and I didn't get a bonus. And I'll tell you what they told me. They said, "Well, the feeling of top management at Agilent is that inventions happen by chance, and that it's times at bat." These are their words. And if enough engineers swing the bat enough times, someone will hit one over the fence. So
So it's all random.
yes, so I decided I don't want to. I think I'm old enough to quit. I think it's time to quit. So I still wanted to make some retirement money, so I did a startup with two other guys. We started Cambotics, which automated TV studios, and this is a picture of one of them. This is a network station in San Diego. We made these robots that would carry these heavy cameras around the floor of the studio, and they were under computer control. So a director could send different cameras to different shots, and they would scoot across the floor and set up the shot. And after about a year or two, we were profitable in the second year, and at that point, I was the VP of engineering. We completed all the designs, and there wasn't a whole lot to do, so I sold out my interest in that and retired for a second time.
So what have you been doing since? Oh, but wait, didn't you get an award for that also?
For what?
For the camera thing?
No.
No, okay. I misremembered then. Sorry.
So you were asking what?
What you've done since then?
Okay. Well, I love to keep building things. As I told you, this is my office. This is my workbench. I've always had a workbench. My wife and I designed the house to be supportive of our hobbies. One thing I did was work. I call it philanthropic engineering. I got involved with a group called Handy Hams that would teach people with disabilities such as blindness and paralysis to get into ham radio as a hobby that would get them out of their confined apartments and so forth. And that presented a lot of questions like, how do you teach a blind person the concept of a square wave or a sine wave or voltage? So enjoying building things, I made a Braille voltmeter that would read voltage, and you could connect a function generator into it and show a sine wave, and the thing would go back and forth like this. Nice sine wave. And you could put a square wave in it and it would snap, snap, snap like that. And so people could feel this. I called it a Braille voltmeter. They could put their hands on it, feel this go back and forth, and practice identifying what the wave shape would be. So I did a whole number of these things. I did a puff and sift telegraph key that would let them send Morse code with their mouth when they didn't have the dexterity to do it with their hands. So, and I did a video for the camp program they had. I enjoyed producing that. So
this was like a summer camp kind of thing for
yes,
for kids and adults.
mm-hmm.
So you combined your ham radio with with extra engineering for
Yes.
for handicapped.
So I still build things. I build another Tesla coil to a higher standard. I love photography. I did the photography for a coffee table book by an artist. Can't think of other things, but
Well, you keep yourself busy.
yeah. Well, I actually one thing I did was start. I don't think this will appear on the camera, but I started replicating some early radio transmitters, such as the one up on the top of the shelf there, and I did that one because it was one of the most popular transmitters in 1929, and yet it was the least understood. And even the experts like Terman basically just hand waved how it worked. They didn't understand it. So so that was interesting. So basically,
Did you write that up? How?
I did. I published that in a radio magazine. Yes.
Okay.
I like to write. So basically, I still do engineering. The difference is that now I get to choose the projects.
Very good. Okay, thank you very much, Gary.
Thank you.